All right, I was finally able to do these DIL injection techniques, and it took me a couple of weeks to get it working. I was only able to do it largely because of the Flare VM. Now, the Flare VM includes not only all these malware analysis tools, it includes some Microsoft build tools. The 2015 version, but anyway, you can compile your own code using the Microsoft compiler. So here's a very simple Hello World program, just a few lines of C++. You can show you compile it in Windows. You use CL/EHSC for just an ordinary plain compiling of hello. And now you've got a simple program called hello. So if you examine it in PE view, you see it starts with MZ and has all these sections: text, RData, data, GFIDs, and relocation. And if you look at the image NT header section, you'll see the time date section, and then you'll see the image optional header, which is where we really want to go. So the image optional header here points to the image base. This is where code loads. Normally, Microsoft code wants to load at a virtual address of 400,000 in hex. That's where all Windows executables think they are running. They each see a file system that is virtual. It's not a real file system, so they cannot reach the memory of any other process. They see, 4 gigabytes of RAM, but they're really working in a little sandbox where that's only their RAM, and they all think it's at location 400,000, but it's not really. And then you have the size of the image and the import table, which is where we want to go. So the import table starts down here. There's an export table and an import table. And the import table is what executables use mostly because they don't provide service to other programs, but they use other programs like libraries. And that's where we're going. So if you go look at the import table, it looks like this. You've got an import address table here. And so we'll play with that a little later. All right, and there are section headers for each section. All right, but you can calculate the memory layout from the memory addresses of each one and find out the code in the executable file on the disk does not map one-to-one to the memory layout. The actual memory layout will take these sections and expand them a little and lay them out. So in the actual file, they can be rammed together, but they get spaced out a little, so they always end on even thousands. So here's how the running program looks in Ollie Debug. You have the PE header, and then you have at 10,000 in, you have the text. At 7,000 in, you have the R data. 2,000. These are here. 60,000 is the header. 61,000 is the text. Then 71,000 is R data, and so on. They're laid out in real memory in accordance with these parameters. And so the import address table is the thing of greatest interest to us. This has the names of all the Windows API functions that this program uses. And even that simple hello world imports uses dozens of Microsoft library calls, and here they are. So all these are Windows API calls, and at the very end, you'll find the DIL they come from. All these come from one simple DIL. So that shows you the structure. Microsoft executables refer to libraries which are dynamically loaded, and the whole point of them is to make the code smaller and to make it load faster and run faster and consume less RAM. So if you write a program that opens up a box for the user to type in something, then that's using user32.dil or something like that, and you don't load your own copy of user32.dil. You query the operating system, and it says, oh, somebody else has already loaded user32.dil. You'll just connect to that DIL that's already in RAM. So many programs are sharing the same code, and you can request a DIL, and it will load that DIL at runtime. So this means Microsoft software is more efficient, but it also means it's very easy to trick it into loading dynamic code with DIL injection, where it loads the wrong code. And that's the most popular way malware runs extra code. So you get this program called Hello4. This is just another plain print, and you see the import address table calling all these things. And if you scroll to the bottom, it will show you that all those things come from kernel32.dil. At the end of the imports, it has the name of the library it comes from. So you can see the addresses and learn how they lay out and see them in a hex editor. And here can see how it looks when you're actually running it. Now, if you run executables on a modern version of Windows, they all have address space layout randomization turned on, so it will load up at some random address. And that's fine for normal use, but when you're analyzing malware and trying to modify code, it's nice to turn it off. So Didier Stevens wrote this handy tool called Set Dell Characteristics that will turn off address space layout randomization for a program. You can just run this program to remove the dynamic base, to change dynamic base from 1 to 0. And now when you run the program, it will actually really load at location 400,000 instead of moving around, which is very handy. All right, so you can examine the kernel. So now you can download a file and you can find out what DLLs it uses for a flag and so on. There's a couple things you can do to practice. And there's ones here where you can fix them because they're trying to load the wrong DLL or the DLL name is damaged, things like that. So you can begin to fix broken code. But what's really fun is DLL hijacking. And like I say, it took me a week or two to figure it out. A lot of people are doing this, but the tools out there are not easy to use. So you have to have Metasploit. You can put it on Windows or Linux to create some malware. Metasploit will let you create malware. MSF Venom is their command line tool. So this will create a shell bind malware, which will just listen on a port, and anybody that connects to that port can execute commands. And you can output a DLL. So I output a DLL called shellbind.dll. So instead of being an executable code, it's a library code. And if you can trick a program into loading this library, it will run that code. Now, when a DLL loads, it runs a process called a function called DLL main automatically. And this Metasploit tool creates DLLs that only have DLL main. They don't actually export any functions. So they're really pretty lame shell DLLs that do not provide any actual functionality. So not very many programs are broken enough to fall for that. But one of them that is this Microsoft service called MSDTC, Distributed Transaction Coordinator. It does something to do with databases, but it's included in Windows 10 by default, and you're almost never using it. So if you run this Distributed Transaction Coordinator, if you just stop it and restart it, and then go to Process Monitor and watch what library calls it makes, you could get all the actions that contain that executable name and that involve DLLs. And you will see that it tries to open oci.dll and it does not find it. I'll make my window a little bigger here. There we are. Name not found. All right, so this is interesting because the process really starts. So what this tells you is this program includes a library but then does not use it. So they accidentally left an include statement in there. Or perhaps it's a second or third order dependency, but anyway, they load a library, but they don't actually use any functions in that library. So then that means you can actually get away with replacing it. You take this malicious DLL and just copy this shellbind into oci.dll where that missing library is, and now when you restart that process, it's going to run a shell. So that's one way to inject code into a process if you can find a program that is cooperative enough to actually try loading a DLL and then not using it. But in most cases, it's not going to fall for that, and you have to do DLL proxying. And DLL proxying is very nice once you get it working. Now here you actually, when I did it, I just did it with Visual Studio 2019, so you have to install that. But you can make your own DLL, and it turns out to be pretty easy. So there is a tool to attack, and the tool we're going to attack is a BGInfo tool. So BGInfo is just another Microsoft tool that prints information on the desktop about your machine. There's nothing that special about it, but it happens to have a vulnerability we're going to exploit here. So if you run BGInfo and view it in Process Monitor, you can see what it does. And notice if I run it from, say, the desktop, these other DLLs load from C Windows System 32, but this one called version.dll, it first looked at my local desktop, and then only when it was not found did it go to C Windows System 32. So that means the mistake of this DLL is it doesn't know the path. And it's dumb enough to look and hunt for that DLL. So again, I have an opportunity to trick it by putting a DIL in the same directory I load it from, which, by the way, is one of the tricks that Stuxnet used to attack the nuclear isotope separators in Iran. And so I can put a DIL here and trick it into running that code. So let's try that. You use Metasploit, which you've already got. You make another DIL called version.dil, and then you try running that. And when you run it, it goes on the desktop and loads the DIL, but then it queries information about the DIL, and it does various attempts to use that DIL, and then it crashes, saying, I can't start correctly. Because the problem here is it's actually using that DIL. And when you give it a fake Metasploit DIL and it loads it, it catches you and says, this is not a good enough DIL. I can't use that. So you have to make a better forgery of a DIL. And that turns out to be pretty easy to do. You create a DIL proxy. What you do, you download an export viewer, so you find out what functions it's using. And you'll see here are all the functions that are actually used. There's about 12 or 15 of them. Get version size. These are the actual functions that that program looks for in that DIL. So and in fact, I think these might be all the functions. These are all the functions that DIL has entirely, not necessarily the ones that program uses. We're going to make an imitation DIL that will fool any program that uses this DIL. So here's all the exported libraries. And now all you have to do is run a little Python script just to rearrange the format to create this file, which is, this is C++ pragma statements, which do this. When it exports a name named getVersionFileInfo, which is the API call. And if I get a call to that API, I will just forward it to something called version_orig here. So I'm going to make another copy of the genuine DIL called version_orig.dil, and I'm just going to forward all the API calls over to that other function. So I don't have to read or understand any of the code. I just forward them all. So this is like a proxy. My DIL sits in the middle, and all real calls will go here. So I can make that in my DIL main, and then I can also add malware. So you put all that stuff at the top of it, you put all that extra code here that does all the forwarding to the real DIL, and then you put malware in DIL main. DIL main is the program that is run as soon as a DIL loads. And here, I add a function to DIL main called exploit. And the exploit function is here, and all that does is it calls a batch file called payload.bat and runs whatever's in there. So this gives you a fully functioning DIL that will totally do anything the original DIL does, plus one extra thing when it loads, anything you put in this batch file. And you just compile it with Microsoft's Visual Studio. You can just compile it right in there. And so you can put something in the payload.bat file, and I just put echoes1 to a desktop file called pwned just to show that it's working. So it's just going to mark the file. So now you build it in Visual Studio, which turned out to be pretty easy. It took me a while to learn how to set the right parameters, but Visual Studio is, of course, how you make Microsoft software, and it's really not very hard. You can create a library, and you just have to tell it what you're doing, give it the right name, set the version numbers and so on, put in that code, and build the DIL. And you end up with a long path to something called version.dil, and then you just have to copy it. So remove the old version.dil that we made using MSF Venom, because we're not using it anymore. Put the original version.dil in there with the name version_orig, and then put in the version.dil you made in Visual Studio. And now, when you run the malware, it's going to look for it, it's going to find it, and it's going to happily use it and write this file on the desktop. So this is all the rage. Everybody's using DLL Proxying, and there's about a dozen different projects on GitHub making tools to do it. And I had a lot of trouble patching together a few tools until I got something that actually worked. As usual, when something is fairly new, all the tools only work on one version of things. But this is, anyway, this is a real powerful technique, and it's the weakness of this dynamic loading. And Caitlin tells me that this dynamic loading is now used also in Linux. So you could probably do something similar in Linux. I haven't tried that yet, but this is a fun thing to do.
Well, it's not just now. Linux uses shared object files.
Yeah.
So, you know, it's. But that's
Yeah, I
fine.
know Linux used to use static linking, where it would make a second copy of its own copy of the library for each process, but apparently they knocked that off.